This circuit analysis example will show one method for analyzing a circuit containing resistors in parallel and in series. A different method of analyzing the same circuit will be shown in circuit analysis example number 2. To start with, begin to think about the current through each of the resistors. Mark it on the diagram. The current through resistor 1 flows through like this. We'll label that I1, which means the current through resistor 1. Oftentimes, beginners get a little worried about the direction of the current. I'd like to show you that it doesn't matter. So I'm going to mark the current through R2 in this direction. Even though I know it actually goes the other way, it's not a problem if you mark it going the wrong direction. When we solve the equations for the current I2 will show up with a negative sign. The negative sign just indicates that the direction is reversed from the way we set it up. It's not a serious mistake. The negative sign tells you what you need to know, so you don't need to worry too much about the direction that you choose for the currents. Finally, I need to mark current 3, which is the current through resistor 3, like this. My next step is to visualize certain current loops. This will let us actually write up our equations using voltage law and current law. There are 3 possible current loops in this circuit. The order in which we analyze them doesn't matter. So the first current loop I pick is going to start at the battery, travel through resistor R1, travel through resistor R2, and then take this wire and return back to the battery. Using Kirchhoff's voltage law, I can set up an equation for the sum of the potential differences along this loop adding up to be 0. So my first potential difference is beginning at the battery. So from the negative terminal of the battery to the positive terminal of the battery is a positive change in potential, and that change is equal to the EMF. Next, when I reach resistor 1, according to the direction of current that I've drawn as I traverse this through my loop going from the top of R1 to the bottom, that will be a decrease in potential. So whenever you cross a resistor in the same direction as the current direction you've chosen, you get a negative change in potential. We can call that V1 for now, the potential difference across the resistor R1. Continuing on this loop, I'm going to, at the branch, choose to go to the left through resistor R2. The current direction I chose for R2 points to the right. We're going the opposite direction through this loop as the direction for the current. So that's going to produce a positive voltage change that we'll call V2 because it goes through resistor 2. And then the wire back to the battery doesn't produce any voltage change. So the sum of all these things has to equal 0. Using Ohm's law, V equals IR, I can go ahead and rewrite this equation in terms of current and voltage. That's it for loop 1. So let's find another loop. Another loop to consider begins at the battery, travels through R1, but at the branch continues straight down the wire, and then comes back through resistor 3, back to the battery. So let's write the Kirchhoff's voltage law equation for this trip. The potential difference across the battery is equal to the positive EMF. Then the potential difference across resistor 1 is negative because we're traversing in the same direction as the current I had chosen. And the same goes for resistor R3. So the potential difference across resistor R3 is also negative because we're traveling in the same direction as the current. So again, just like with the first loop, we're going to rewrite this equation using Ohm's law to write it in terms of current and resistance. So loop 2 has been analyzed using Kirchhoff's circuit law. Now it's time to take a look at loop 3. Loop 3, I'm going to begin with the junction on the left, travel through resistor 2 and around, and then travel through resistor 3. So I need to write the voltage law equation for this loop 3. The battery is not a part of this loop, so we begin with just the voltage change across resistor 2, and then the voltage change across resistor 3, and that's all we've got. For both of those, we're traversing the resistor in the same direction as the current I had drawn, so both of those are negative. I can rewrite this using Ohm's law. So V2 is I2 R2. V3 is I3 R3 because V equals IR. And already there's some hint that I've chosen something that's not quite right because we have two negative quantities and we're putting them together to equal 0. So one of these quantities actually needs to be positive and the other negative in order to sum them and get 0. But don't worry about it. Like I said, when we solve for this, we're going to discover that I2 comes out of these equations as a negative current, and the negative sign will just tell us that that's the arrow that was pointing the opposite direction from the actual direction of the current. It's not a big deal. It's not something you would lose points for. It's correct that way, as long as we do it carefully so that the negative sign turns out. That finishes the voltage law analysis of the circuit loops. The last thing I want to look at in this part 1 is to take a look at how the current law works. If we take the junction on the right, we can look at the current flowing into the junction and the current flowing out of the junction. The current law tells us that the current flowing in equals the current flowing out. The way I've selected my current directions, the currents flowing into the junction are currents I1 and I2 that both flow into this junction on the right. The current that flows out is current I3. Although it's marked over here, it has to travel all the way through these wires to get there. So the outflow is I3. With the current law equation, we've finished part 1, which is all of our setup work. So the equations that will carry forward into part 2 include these 3 voltage law equations that we developed using the circuit loops and the Kirchhoff voltage law, as well as this current equation that we got using Kirchhoff's current law. So that's the end of part 1.